Hey guys, welcome to Thermodynamics Part 6 on the ideal gas law. As discussed at the end of the last video on thermal expansion, the ideal gas law can almost be seen as a version of thermal expansion in 3 dimensions, but for a gas rather than a liquid or a solid. Now, at the end of the last video, I challenged you to go to fet.colorado.edu and to take a look at their gas properties simulation to explore some of the relationships between the variables, specifically looking at temperature and volume, and seeing how pressure and other factors play into the development of this law. So if you haven't had a chance yet, I highly recommend you go back and take a look at it. It will give you a lot more visual and conceptual understanding of what we're talking about in this video. After all, the ideal gas law is one of the fundamental ideas that we will use for a large portion of the remainder of this thermodynamics series. Let's get into it. So the story of the ideal gas law starts in 1662 when Robert Boyle discovered the correlation between pressure and volume. About 100 and so years later, in 1787, French physicist Jacques Charles discovered the correlation between temperature and volume. Gay-Lussac's law was then established in about 1805 to 1810, where we related the pressure and the temperature of the gas to one another at a fixed volume. And finally, very shortly afterwards, Avogadro's law in 1811 related the amount of gas and the volume of the gas, assuming a constant temperature and pressure. These 4 laws combined together create the combined ideal gas law. Now, they're all related by proportionality constants, either the gas constant or the Boltzmann constant. Now, we already took a look at the Boltzmann constant in an earlier video when we were trying to come up with the definition of temperature. And what I think is so cool is that this constant relates so many different areas in thermodynamics and beyond to one another. Now, something very important to keep in mind is that we're dealing with an ideal gas. This gas is simplified a little bit, but it does provide the foundation for real gases too. Now, we need to keep in mind that this gas that we're talking about in our examples over the course of this video and the next several are ideal gases that follow the kinetic theory. In other words, there are many particles, they're moving in straight lines, having collisions randomly. They will not lose any kinetic energy during their collisions, so they're perfectly elastic collisions, and the gas will not combine with other particles within the gas. So we will develop a law later on to relate a monatomic, diatomic, and polyatomic gases, because after all, they are slightly different, but they all do show the same basic relationships between pressure, volume, temperature, and the amount of gas. So we'll get into each of those in a little bit more detail in this video, and then more in the next. So let's start by going in depth and looking at Boyles Law. Now remember, Boyles Law relates pressure and volume. And what we find is that if you hold the temperature of the gas constant and the amount of the gas constant, you find an inverse proportion between pressure and volume. Another way we could say that is that pressure is proportional to 1 over the volume of the gas. A third way to look at it is to say that the product of pressure and volume is constant at a given constant temperature, of course. Now, the way that this data is obtained and the way that you can think of it is that you have to remember that a gas fills the volume of the container that it's in. So if I expand the volume of the container, we see that the pressure drops. Now, this relationship makes sense, I think, because if there's more space with the same number of particles and they're moving at the same average kinetic energy each, they will collide with the walls less often, therefore having less pressure. Because after all, the pressure is registered by the amount of times and the force that the gas interacts with the walls of the container. So as the volume increases and there's less often collisions, we'll see that the pressure overall will drop. Now, this pressure-volume relationship becomes extremely important when we are dealing with heat engines, which we're going to take a look at down the line in a few videos, and really unpack how you could have an engine cycle that can be described through the relationship between pressure and volume. Next, let's take a look at Charles' law. And Charles' law, remember, says that there's a direct correlation between temperature and volume, assuming that pressure and the amount of gas in the system remains constant. Now, this was always the most confusing law for me, because the way my brain saw it was that if I have a container that is fixed in size because we can't let any gas into or out of it, and I increase the temperature of the gas, I knew that the particles' average kinetic energy should increase as well, which means they would collide with the container walls more often and thereby register a higher pressure. So how could I increase the temperature and cause the volume of the gas to expand when the volume is fixed? The gas fills the container. It can't fill any more space than is already there, and therefore the pressure is just going to keep going up. Now, this is true. This would happen, but we're forgetting one thing, that if we increase the temperature and we say that the volume increases as well, that must mean that there has to be some sort of expandable container. In other words, I have to be able to match the volume of the container to the volume of the gas, because those are two different things that we sometimes have to assume are the same, especially because we identify that a gas fills the container that it's in. So the way that I began to look at it was like this. Let's assume that we have a container, it's a cylinder, and it has a fixed bottom to it, but the top of it is a lid, if you will, that fits directly on the inside and is lubricated to avoid friction. But basically what can happen is that as the gas inside this cylinder in this container expands, it can push that sliding lid or top up and down as it shrinks and expands. Now, it can't completely come off, so we'll have a way for it to be fixed on the container, so there's a maximum volume. But in this case then, as I increase the temperature and the particles' average kinetic energies increase, they will expand and apply pressure, also known as force per unit of area, to that movable lid, which will cause the volume to expand. So it's basically a way to keep the pressure constant while preventing any gas molecules from escaping. Because you could see another way to keep the pressure constant would be to have some sort of exhaust, right? As I increase the temperature of the gas and the gas started to expand, we could release gas molecules so that the pressure would always stay the same. But Charles' law says that if the pressure and the amount of gas is also held constant, then I see a direct relationship. So I have to make a movable top to this container in order to make the volume actually expandable. Because if the volume cannot expand and you increase the temperature, then we see the pressure increase. And that's actually another relationship that is seen in the ideal gas law. Another way you can look at Charles' law is flip the volume and the temperature. Say that the volume now is the independent variable and the temperature will have to be dependent. Now, it doesn't really work that way, but let's take a look at it like this. If I expand the container walls through some other mechanism without actually increasing the temperature in order to do that, so in other words, I just make the container bigger, well, the gas fills the space, and as we just saw in Boyles' law, the pressure drops because they're going to be hitting the container walls less often. So how do I then keep the pressure constant according to Charles' law when expanding the volume? Well, if you think about it, if I have to keep the same number of collisions with the container walls in a given amount of time, and I've expanded the volume, I would have to increase the temperature of the gas. So I'd have to get the gas molecules moving faster so that they could collide the same amount of times that they were before, even though they're covering a greater space. And in doing this, I'm keeping the volume and the temperature a direct proportion, and therefore keeping the pressure the same. So there's many different ways to look at these, and as we learn how heat engines work in the next few videos, we're going to really need to internalize these ideas and keep in mind, what can I do? How can I be creative about keeping something constant as other variables change? For example, one issue that we overlooked, for the eagle-eyed among you, you may have noticed that if the volume expands and the pressure drops, how come the temperature is not dropping too? Well, we'll get to that. We'll get to that in one of our next few videos as we start to discuss what's the actual process in achieving these ideal gas relationships. Because after all, when we study them sometimes in intro chemistry courses, we oftentimes don't go into the details of how these things are being held constant. Next, we're going to take a look at Avogadro's law. Now, Avogadro's law relates the amount of gas to the volume of the gas. But to me, on a whole, that's very misleading if we just look at it from that perspective. Yes, that is true, but let's take a look at it from a more novel approach. So let's say that I have two containers, and both containers have the same volume, and they both have the same pressure, and they both have the same temperature of the gases that are contained in each. What Avogadro found was that if all those things are the same between the two containers, I must have the same amount of gas in both containers. So in order to achieve the same volume between, say, two different gases at the same pressure and the same temperature, I will have to have a proportional number of molecules or of moles of the gas, so an amount of the gas, in order to keep the pressure and the temperature same between the two gases. Now, this idea to us is maybe kind of obvious, but at the time, the idea that a system is made up of a lot of particles or little pieces wasn't as completely understood and accepted as it is today. Finally, we look at Gay-Lussac's law. Now, Gay-Lussac's law states that the pressure of a given amount of gas varies directly with the temperature of the gas, but this only occurs when the volume is kept constant. Now, I think this makes a lot of sense from what we've talked about with the ideal gas theory so far, that when I increase the average kinetic energy of the particles of the gas by adding heat to the system, the temperature increases, and if those particles are moving faster, they'll collide with the walls of the container more often, thereby increasing the pressure as well. Now, we've overlooked the processes that allow all of these different sub-laws of the ideal combined gas law to occur. We're going to take a look at those in great detail in the next few videos. Now, many intro chemistry and thermodynamics students might refer to the ideal gas law as pivnert. And I'm not a huge fan of that, although I think it's a great way to remember the ideal gas law, or at least the way you need to remember it when you are a high school chemistry student. But it forgets about the fact that the Boltzmann constant, K sub B, could actually be part of this law. I could rewrite the ideal gas law as PV equals uppercase N, K sub B times T. Now, this is clearly not pivnert anymore, and I don't even want to try to pronounce some sort of way to remember that one. But the difference between the two is really very simple. Lowercase n is referring to the number of moles of the substance of gas. So the ideal gas constant, 8.314 joules per Kelvin mole, is looking at more specifically a relationship between moles and the other variables. Whereas PV equals NKBT is actually relating the number of molecules or particles of the gas, uppercase N, to the Boltzmann constant and the other variables. Now, the Boltzmann constant is something that we got into a little bit of detail when we looked at what temperature was actually measuring, the average kinetic energy of a particle within the gas. And that's why in thermodynamics, the version of the ideal gas law, PV equals uppercase N K sub BT, is actually oftentimes a lot more useful because it's going to allow us to look more at the physical side of things as individual particles rather than just as a mole of the gas overall, although both are very useful. Now, obviously, we can relate the ideal gas constant to the Boltzmann constant by using Avogadro's number. So if I take the ideal gas constant and I divide it by Avogadro's number, which is describing the number of particles in the mole of the gas, I end up with the Boltzmann constant. And the Boltzmann constant here obviously can be multiplied by Avogadro's number to get the ideal gas constant. So in physics and in thermodynamics, it's oftentimes more useful to use the Boltzmann constant, because what we are going to see in a few videos down the line is that when we look at the microstates of the gas and we're looking at individual particles or statistical groupings of particles, it's oftentimes helpful for us to use the Boltzmann constant because it links to some other statistical mechanics ideas that the ideal gas constant usually won't. So we just crammed a few hundred years of physics and chemistry into a several-minute video where we put 4 different laws together. We looked at constants and Avogadro's number and all sorts of things that gave us a headache in intro chemistry. But what we want to do is take a step back and relate the ideal gas law to common sense. From one perspective, the ideal gas law basically says, if you take this container that is not expandable and you pump a whole lot of gas into it, at some point the pressure is going to get so high that it will burst. Or perhaps we could look at it from the perspective of a tire. If I pump a tire full of air, I will see the volume increase of the tire. At some point when the volume can't increase anymore, the temperature and the pressure of that tire will start to go up. Now, in thermodynamics, we're going to take this ideal gas law and we're going to put it to use. We're going to look at how we can expand the volume and keep the temperature the same, or how we can keep the pressure the same in a system where we're changing the volume. So when we use this, we're trying to get some work out of it. In other words, a heat engine. We're going to take a look at the theoretical ways in which an engine works using this ideal gas law. So I leave you with a challenge. At the beginning of this video, when we looked at Boyles Law, the relationship between pressure and volume, I specifically did not address something that I think is fundamental to the next steps we take, and that is the following. If I increase a fixed amount of gas to a larger volume, I know the pressure is going to drop. That makes sense. But Boyles Law assumes that the temperature is constant. So what process would I have to engage where we will expand the volume and let the pressure fall, but prevent the temperature from falling too? I want you to try to figure that out. Then come back to the next video. We'll take a look at the answer to that and investigate a few other things in how we can make the ideal gas law useful to us.